Thank you, Jay. I think we should have some time for further questions during the summary and wrap-up session. But I'd like to move on to our next speaker. The panelists, the speakers in the first panel gave us a good overview of the problem. Jay has talked more about measurement techniques through GRACE. And our next speaker is going to give us yet another perspective on the problem. We'll talk about land subsidence. She's Michelle Sneed. She's a hydrologist with the U.S. Geological Survey in California. Her background is geology. She uses various methods to measure land surface elevation, including InSAR techniques. And her recent studies in California have explored the impact of subsidence on water conveyance infrastructure. She's a member of several professional organizations and also the UNESCO Working Group on Land Subsidence. Michelle?
Thank you very much. Very nice to be here today among this esteemed cast of characters. So I'm going to talk about land subsidence. So yeah, the sort of bad news train that Jay mentioned is going to continue. Unfortunately, we don't have a lot of good news. If you've ever seen anything about land subsidence, then you've probably seen this photo of Dr. Joe Poland. He worked for the USGS, and he's using a power pole to illustrate where the land surface was in 1925, 30 feet above his head, 1955, and where he's standing in 1977.
Where is this?
This is southwest of a tiny town called Mendota. It's not far off of I-5, which is in California, which is a major transport backbone. So we've redone this. We couldn't do it in the same location that Joe Poland was standing. I mean, we could have, but it wouldn't have conveyed the message that we want to convey, and that land subsidence is still a problem. It was essentially fixed, for the most part, where Joe Poland was standing by introducing water conveyance and bringing more surface water to that area, and I'll go into that in a minute. So if we did that picture again from 1977 to 2013, the 2013 sign would have been only about 2 feet lower, so kind of anticlimactic. Wouldn't have really made the point. But here, I'm standing on a highway, 152. It's a major east-west corridor in the Central Valley in California. And it's showing that I have, about the time I graduated high school, the land surface was about at my head. And in 2013, it was about 5 feet lower. I just looked at data last week, and this site has lost another about foot or foot and a half of land surface elevation. So to get us just on the same page, land subsidence is either a gradual settling or a sudden sinking of the Earth's surface. So it's a lowering of elevations. And while there's many causes of land subsidence, some of the famous ones are sinkholes that you might see in Florida, eating houses and trucks in mere moments. Most of the identified mileage that's affected by subsidence in our nation is a consequence of our exploitation of groundwater, so overuse of groundwater. And almost all of that is caused by the compaction of the aquifer systems where the water is withdrawn. So looking at the nation as a whole, you can see that these dots represent areas that where land subsidence has been measured. And you can see a lot in the Southwest. That's not a huge surprise. We don't have a lot of surface water in the Southwest. It's dry or quite arid, so we use groundwater for most of our water supply. But we also have some problems on the Gulf Coast. This is from groundwater pumping as well as oil and gas. Just another fluid causes the same process of compaction. So that's a problem because you're right next to the coast. Same thing with Chesapeake Bay. While we are seeing land subsidence rates in California upwards of 1 foot per year, which is extraordinarily high, among the highest rates in the world, Some data I've seen recently, which I'm hoping is preliminary and will be revised downward, would indicate that we are far exceeding subsidence rates anywhere in the world by a long shot, including Tehran, including Jakarta, places that are subsiding very quickly. But on the East Coast, there are very small amounts of subsidence. We're talking about a few millimeters per year. The problem is that we have a whole lot of assets right on the coast, economic, cultural, population centers. So along with sea level rise and land subsidence, even just small bits, we're going to start seeing increased flooding. And in fact, we've already started to see increased flooding in terms of new locations and the depth and duration of flooding. So it doesn't always necessarily matter how much subsidence you have, but where that's occurring. So scoping down to California, I work in California on subsidence problems most of the time, but I am working also in Virginia and Texas. Again, this is just a blow-up of that last map. We have lots of areas that have been identified as having subsidence issues in California. And I'm going to focus on the San Joaquin Valley. This is where we've built huge conveyance systems because most of the rain and the snow falls in the northern part of California, but most of our farms and population centers are in central and southern California. So we've built these massive conveyance systems to move the water from north to south. And that's because we grow a lot of food in the Central Valley. And you can see here that this is a very flat area already. And the impacts of subsidence on these kind of conveyance canals, right? They're built in these very flat valleys on very small gradients because it's less expensive than to build them up. We like to use gravity to move the water. For gravity to work, every point upstream has to be higher than every point downstream. And land subsidence is changing that and impacting the ability to deliver surface water, which of course puts even more demands on the groundwater. This is a photo of a well, and if you've ever poured concrete, you don't ordinarily pour it in air like that. That's engineer that, eh? And the reason it's sticking up out of the ground, here's a bucket for scale, is that this well casing is at depth. And it's essentially holding itself up as well as the concrete is attached to the well casing. If it hasn't already happened, this well will collapse. Usually collapses in the screened part of the well because that's where the water comes in, and there's holes in that part of the casing, so it's the weak point. So how does this aquifer system compaction work? So when sediments are deposited, and clays are a platy mineral, so this is different than sands or gravels. You know, if you've picked up beach sand, it's pretty round. Clays are different because they're a platy mineral, and when clays are deposited, they're generally deposited in this kind of random orientation. And you can see that there's a lot of space between these grains to hold water. And people don't ordinarily think of clay as being a great storer of water. But in fact, it stores more water than any other kind of sediment. It doesn't transmit it very well, but it stores great quantities of it. When we start lowering groundwater levels in a chronic way, then these clay grains will actually start to respond to this new stress. It's called the pre-consolidation stress, but it's really estimated as the previous lowest groundwater level or the highest amount of stress at any point in the aquifer system. When we exceed that threshold, these grains rearrange themselves, and two things happen. One is that it takes up less space, so those clay units get thinner. And the other consequence is that you can see that there's a lot less space between the grains to store water. That space is never going back to that. That's permanent. That's called inelastic compaction, and that's the kind of compaction that we worry about, the kind that's permanent. As water levels go up and down, aquifer systems, we call it kind of breathe a little bit on a seasonal basis. As water levels come up, these pore pressures in here get higher, they push the grains apart. And that's true in sands and gravels and everything else that's saturated. And then when the water levels decline a little bit in the summer and fall, it gets a little bit thinner. We have a little bit of this sort of elastic response going on. But it's this chronic lowering that causes this inelastic compaction, and it reduces the storage capacity of the aquifer system. Okay, in California, we've built reservoirs in all of the best places already. It's not that we can't raise them a little bit. Maybe we could build a couple of more, but we're really out of space for surface storage. And some places in California, as Bridget showed, are already recharging the aquifer system. They're using it as a managed aquifer system, a managed reservoir, just like a surface reservoir. And just like surface reservoirs silt in and lose capacity to store water, at least you can dredge that out. You can get that silt out. You cannot get this storage back. So we're impacting the ability of our future managed reservoirs to store water. So I've gone through a lot of this already. So in addition to this sort of reduced storage capacity, right, that's sort of a natural resource problem that people like water resource professionals think about the future and what we're doing to the aquifer system now. Most people think about money. What is this costing me? So, but we have these huge problems with these canals, as I mentioned. Canals are the most sensitive because they're built on these slight gradients. And as soon as we're not lowering the land surface evenly. If we were, all of those gradients would be maintained. Nobody would care. I wouldn't be here. But because we are lowering it differentially, we're impacting the ability of these canals to move water. So usually when you stand on a bridge, this is a bridge over a canal, you expect to see the water flowing under the bridge. Well, here it's flowing into the bridge, and that's because of subsidence. It's also because we use gravity to move water. So the water surface elevations in these canals have to be kept at a certain level to keep flowing where they're supposed to flow. So we have to build up bridges, we have to build up levees. Essentially, these canals are getting deeper because we're building up the sides so that we can keep the water surface elevation at a level that will allow it to continue flowing downhill. This is a photo of a canal that has a buckle in it. Well, we can't say for sure that that buckle is caused by subsidence. This area has been very problematic for a long time with subsidence. This is a well that is in an active vineyard. So they paint the part that sticks out of the ground orange so that equipment doesn't hit it. Well, in a 2-year time period, 2 more feet of this well casing are exposed, very similar to the protruding well I showed you a couple of slides ago. They just keep cutting it off so that equipment doesn't hit it. While I've been talking a lot about canals, it's really any linear feature that crosses these areas of differential subsidence that aren't flexible. That includes roads, pipelines, railways. I'm working with the California High-Speed Rail, who is building a rail line right through the worst of the subsiding areas in California, and they are having to contend with this as an engineering problem. And then, as the land is lowering in different places at different rates, wetlands and rivers are in the lowest places of the land. That's where they are. So we're seeing, impacts to wetland and riparian corridors, and of course the ecosystems that depend on them. All right, so a little history of subsidence in the San Joaquin Valley, where the Joe Poland photo essentially came from. There used to be subsidence on the west side of the valley. So here's the whole San Joaquin Valley. There used to be subsidence on the west side of the valley. Well, you can see here these green lines here are engineered canals to move water around. And here, in this location, we have some time series data. And the upper graph is groundwater levels, and the lower graph is compaction. And you can see that water levels were declining and compaction was occurring until around 1970. Well, that's when the California aqueduct started to deliver water. And so water levels recovered, subsidence compaction essentially stopped, except during droughts, right? So here's the 76, 77 drought. We saw water levels crash 150 feet in a very short period of time. After the drought was over, we saw compaction reinitiate. Water levels recovered until the next drought. So we thought, with these latest droughts, we kind of wondered what happened. We essentially, mostly fixed the problem except for when not enough water was coming down the canals. So we're now seeing subsidence where these red circles are. It's actually much bigger than that, but those are kind of the areas where most of the subsidence is now occurring. And the next two graphs I'm going to show you, the first one is here, and the next one is here. This is in Mendota. Joe Poland was standing about right there, and this is in Madera. So we thought that we would find the same thing that I just showed you, right? You always say, oh, the past is the key to the future. And sure enough, this is brown is subsidence and blue is groundwater levels. And we could see that, okay, so in between drought periods, there was essentially no subsidence. So maybe we still have this problem licked, groundwater levels declined, yeah, we had subsidence. They recovered, and we didn't have subsidence. So this is what we thought we would find when we started to look at these latest droughts. And we did find it in some locations, but not everywhere. So in some places, we're seeing subsidence occurring even during wet and very wet years. This is concerning, obviously. We thought that we would only have subsidence during droughts, and as it turns out, that's not true. And it has to do with who has access to the surface water and who doesn't. And I'll show you a graph here in a minute. So this is where we're seeing subsidence. And so this is a 2-year period, only 2 years. And we're seeing a maximum of 21 inches there, a little bit less down here, obviously a bigger area impacted. Almost half of the San Joaquin Valley has been impacted by at least 2 inches. Historically, this is where it was. So it's shifted. I'm going to show you a close-up of this area and some time series data that we have. So you can see this area here, lots of subsidence. This is in a really terrible location. This is right between the San Joaquin River and the Eastside bypass. The Eastside bypass is a flood control channel. And it was built to ease flooding on the San Joaquin River. Because in California, we have this enormous mountain range, the Sierra Nevada. Holds lots of snow. But if it all comes down at once, there's no place for it to go. It goes out San Francisco, right? It goes out the Golden Gate. So it fills up this valley unless we can get rid of it fast enough. So that's why the Eastside bypass was built, to ease flooding. And you can see here now that we've got a low spot in this system. So, and this is based on InSAR data, by the way. It's satellite data, radar data that we process that's sensitive in the vertical dimension. And I've just contoured it to make it easier to interpret. So water flows through the Eastside bypass from A prime to A, and eventually out the Golden Gate. And here you can see the problem. So as water's flowing, it has to fill up this hole, and every elevation equal to or lower than it, so hopefully the levees are built up there, before it can continue flowing where it fits into this big hole. And of course, this is greatly vertically exaggerated. So it's going to have to fill up that hole, again, before it can get up over all of this to flow out the Golden Gate. You've seen 2 of these plots before. This is P304. This is near Mendota. This is the one that, okay, subsidence only during droughts. This is the other one I showed you. Okay, so we have subsidence during droughts and it gets worse. Or we have subsidence in between droughts and it gets even worse during droughts. And here is the same situation. This shows who has access to surface water and who doesn't. And the reason that this has changed through time, and we're not sure when it changed, when did subsidence start occurring even between droughts? We don't know when that happened. So this is a result really of land use change. Out here there was a lot of either rangeland that was unirrigated or row crops that you could fallow when times were hard. But what's happening now is we're planting a lot of permanent crops in California that you can't fallow. Pistachios, for instance, take 7 years before you get your first nut. So you have to constantly water that tree to get a nut at 7 years. The two things that you have to have for subsidence to occur are groundwater level declines, and you have to have clay. Without clay, you're not going to get massive subsidence. You're going to get that elastic subsidence that's recoverable that I talked about, but not this inelastic. So we definitely have this. We have chronically lowering groundwater levels. This is just one example. I've been measuring some of the same wells for the last 6 years now, and they've dropped more than 300 feet in 6 years. This is a little bit weird to look at, but it's just boreholes where we digitize what kind of sediment we're drilling through. And so it's the whole Central Valley. So Redding is up here, Bakersfield's down here. And you can see lots of blue, which is clay. We have lots and lots of clay in the San Joaquin Valley. We're starting to drill wells to 2,500 feet. We're starting to engage new clay that has never been really engaged before because pumps were always higher than that. So what can we do about it? And we've talked about this a lot today. We either have to reduce groundwater withdrawal. We have to maintain groundwater levels. It's very simple scientifically. Putting this into practice is a whole other ball of wax. California is going to start to attempt to do that here in the coming years. But you have to reduce withdrawal or you have to enhance recharge. And this is the part that I'm a little bit concerned about because we're damaging our reservoirs before we're really using this on any great level. So that's just a summary of what I've been talking about today. Groundwater depletion in the states, in many parts of the states, is a real problem. It's really exemplified in the San Joaquin Valley. And going back after so many years of not paying attention, because we thought we fixed the problem when the California aqueduct started to deliver water. And so, like with any other problem that you fix, resources go other places. And we stopped looking at subsidence. And when we looked back and started to find a foot of subsidence a year in some places, we were very surprised, and frankly, I was quite embarrassed that we had stopped looking. We really need long-term data to get a handle on these problems and how they're changing, especially with climate change. Now that more precipitation is going to come down as water instead of snow, our Great Sierra Nevada snowpack is going to be reduced. Water is going to come down much sooner than it did before because of less snow. So it's not going to be around in July, August, September when the farmers need it most, and they're going to continue pumping to make up for that deficit. So we don't see the problem getting much better real soon, even with this new legislation in place. Thank you very much.
Some questions for Michelle?
So Asari, Penn State and National Academy. I found your talk very fascinating because my elder brother, Som, knows all about clays and how they change their packing and what makes them change their packing. And Som has been asking some ignorant questions this morning about role of contaminants and so on. And that leads me to wonder if anybody is investigating the role of salinity in this clay orientation and reorientation behavior.
I think there has been some studies out of, I don't think they're American scientists. I can't remember where they're from. But they were talking about how the water quality was changing because of subsidence. And I don't know much about that study, but I think somebody has looked at it. Something that we're concerned about in the San Joaquin Valley is that we do have briny water at the base of the aquifer system. And as we are drilling deeper and deeper, at some point we're going to start entraining that water to move to the pumps. And I don't think that I've heard any reports of that happening, at least in areas, certainly individual wells. But that is something that we are concerned about, but that's more of a function of where we're pumping from.
Hi, Michelle. Great presentation. I have a question.
Bridget, did you just?
Oh, Bridget Scanlon, University of Texas. A recent study that came out by Kang and Jackson suggesting that there's large volumes of brackish groundwater in California. What is the potential for developing that, and what are potential impacts with subsidence? In Texas, we don't even look for brackish groundwater resources where we have subsidence already. So I would like your views on that.
Well, I think it's a matter of economics, right? So if it's all a matter of where you're going to get water for the least amount of money. And right now, that's through canals and through groundwater pumping. But if you have to start treating the groundwater that you're pumping, then prices are going to go up, and there's probably going to be some changes unless they have a big bag of money that they can just, put on per well for treating right out of.
Yeah, but will you induce subsidence when you develop that resource?
That's a good question. We hardly have any data from those kinds of depths because these are thousands of feet deep. Hardly any wells penetrate there. We do have some oil and gas wells, but even those are 2,000 or 3,000 feet deep. Some parts of the basin are many more thousands of feet deeper than that. So we really don't know what is the clay content down there, because that's the question in terms of subsidence. If you're going to deplete the groundwater resource, what is your geologic setting? And if you have clay, then you're going to induce more compaction, which is not fixable. At least the infrastructure we can sort of engineer our way out of. We can just throw a lot of money at it and keep fixing it, but this compaction of the aquifer system is unfixable.
Okay, thank you, Michelle.